Most of us are familiar with the standard narrative of how the universe began. There was an infinitely dense point of an infinite temperature with no size called a singularity. This singularity exploded, creating all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 10 circumflex 36 seconds and 10 circumflex 32 seconds, space expanded exponentially, growing much larger in size. After this period, space continued to expand, but at a much slower rate, eventually leading to the universe we observe today. This is the inflationary Big Bang theory, the most popular and broadly accepted theory of how the universe began. However, for a few physicists, the premier theory doesn't paint an accurate picture of the evolution of our universe. They propose that the universe existed before that point, stretching forever into the past and future. While the universe is expanding today, it was contracting before the Big Bang. In this picture, the Big Bang isn't so much a bang, but a bounce, a moment when a shrinking universe reversed course and began to grow. According to their theory, the universe could bounce again, with today's expansion followed by a collapse in the far future, leading to another bounce. Some physicists suggest this bouncing could be infinite. This challenges the way most cosmologists view it, where everything started with the Big Bang. Renowned physicist Brian Cox also challenges the Big Bang theory, asserting that something cannot emerge from nothing. Adding to the tension, the James Webb telescope has made discoveries that contradict the notion that the Big Bang marked the universe's beginning. These raise the question, if the Big Bang wasn't the beginning, then what was it? Could the universe start with a bounce or something else entirely? Join us as we dig deep into one of the thorniest issues in physics, the idea that the universe had a beginning, or a day without a yesterday, as it was originally known, dates back to Georges Lemaitre in 1927. While it is still defensible to state that the universe likely had a beginning, that stage of our cosmic history has little to do with the hot Big Bang that described our early universe. Many laypersons and even a minority of professionals still cling to the idea that the Big Bang means the beginning of it all, but that definition is outdated. The Big Bang now is not the birth of time and space, as we know today in 2023. Evidence points to a non-singular origin of our universe. We never achieved those arbitrarily high temperatures. Instead, our universe is best described by an inflationary period that occurred before the Big Bang, with the Big Bang being the aftermath of what occurred at the end of inflation. During inflation, the universe was completely empty, no particles, matter, or photons, just empty space with a huge amount of energy fluctuating over time by about 1 part in 30,000. As the universe inflates, these fluctuations get stretched to larger scales, while new small-scale fluctuations are created atop them. This superposition of fluctuations is a defining feature of cosmic inflation, continuing as long as inflation goes on. However, inflation ends randomly and not in all locations at once. If you lived in an inflating universe, you'd likely experience a nearby region where inflation ended while the space between you and it expanded exponentially. For a brief instant, you might detect what happens at the start of a Big Bang before that region disappeared from view. In an initially small region, perhaps no bigger than a hamster ball, the energy inherent to space gets converted into matter and radiation. This conversion is fast, taking about 10 circumflex 33 seconds, but not instantaneous. As space's energy converts into particles, the temperature rapidly rises from near absolute zero to about 10 circumflex 20 Kelvin. Under these conditions, all quanta behave as radiation due to their high kinetic energy. Regardless of whether the particles are massless or massive, this conversion process, known as reheating, marks the end of inflation and the beginning of the hot Big Bang. When the hot Big Bang starts, distant regions recede more slowly as time goes on. From an outside perspective, the expansion rate drops in regions where inflation ends, while surrounding inflating regions see no such drop. The distance to any object would double after a certain amount of time under inflation, doubling again after the same amount of time. But once the Big Bang begins, this expansion slows down. Probability-wise, from the perspective of an inflating space region before the Big Bang, inflation ends in nearby regions many times. These regions fill with matter, antimatter, and radiation, expanding more slowly than inflating regions, leaving you in an inflating region as typical within spacetime. Regions where hot Big Bangs occur will expand away from other inflating regions exponentially, quickly receding from each other's view. In the standard inflationary picture, there's virtually no chance that any two separate hot Big Bangs will ever collide or interact. Eventually, inflation ends for us, and the energy inherent to space converts to a hot, dense sea of particles. The only imperfections correspond to quantum fluctuations stretched across the universe during inflation. Positive energy fluctuations result in overdense regions, while negative fluctuations lead to underdense regions, serving as the seeds of cosmic structure. We cannot observe these density fluctuations today from the early universe, but we can extrapolate back from the cosmic microwave background 380,000 years later. The temperature fluctuations in the cosmic microwave background confirm cosmic inflation story. However, there are inconsistencies between the cosmic microwave background and our current cosmology model, suggesting we're missing something fundamental. Loop quantum cosmology, derived from loop quantum gravity, where gravity consists of particles called quantiforming space-time fabric, proposes an alternative. In this model, space has a minimum size. The Planck scale 10 circumflex 35 meters, meaning the Big Bang couldn't exist. Instead of an infinitely small, dense point, the universe experienced a bounce due to quantum geometry's repulsive force. This implies a universe that contracts and then bounces, expanding and collapsing cyclically. Loop quantum cosmology explains cosmic microwave background anomalies, including hemispherical anisotropy and large-scale power suppression, by incorporating quantum gravity corrections. While confirming loop quantum cosmology is challenging due to cosmic variance, it provides intriguing resolutions to some cosmological puzzles. Moreover, it questions whether the universe had a beginning or is cyclic, challenging the traditional Big Bang view. Cyclic cosmologies suggest an immortal universe with endless bounces. However, entropy presents a challenge, as each bounce increases disorder and decreases usable energy. New cyclic models address this by requiring significant expansion to dissipate entropy. Nonetheless, calculations suggest that even with these corrections, the universe likely had a beginning, implying a Big Bang at some point. The debate continues, with proponents of a cyclic universe yet to respond to recent challenges. Most of us are familiar with the classic narrative of the universe's inception, an infinitely dense, infinitely hot point known as a singularity exploded, giving rise to all the space, energy, and matter that constitutes our universe in an event called the Big Bang. This explosion was followed by a rapid exponential expansion between 10 circumflex 36 and 10 circumflex 32 seconds, after which the expansion slowed, eventually leading to the universe as we observe it today. This inflationary Big Bang theory is the most widely accepted explanation for the universe's origin. However, some physicists challenge this view, proposing that the universe existed before the Big Bang, extending infinitely into the past and future. According to their bouncing universe theory, the Big Bang was not an origin but a rebounder moment when a contracting universe reversed into expansion. This theory suggests that the universe might undergo endless cycles of expansion and contraction, challenging the traditional Big Bang view. Renowned physicist Brian Cox has also questioned the Big Bang theory, arguing against the idea of something emerging from nothing. Adding to the debate, discoveries by the James Webb telescope suggest that the Big Bang might not mark the universe's beginning. If the Big Bang wasn't the start, then what preceded it? Could the universe have begun with a bounce or another unknown process? Join us as we explore one of physics' most perplexing questions. The concept that the universe had a beginning, often described as a day without a yesterday, was first proposed by Georges Lemaitre in 1927. While it's still plausible to say the universe likely had a beginning, this early stage has little to do with the hot Big Bang that describes our early universe. Many laypeople and some professionals still equate the Big Bang with the universe's birth, but this definition is outdated. Today, evidence points to a non-singular origin of our universe. We never reach the arbitrarily high temperatures. Instead, our universe is better described by an inflationary period before the Big Bang, with the Big Bang being the aftermath of inflation's end. During inflation, the universe was empty, no particles, matter, or photons, just empty space with immense energy fluctuating over time by about 1 part in 30,000. As the universe inflated, these fluctuations stretched to larger scales, with new small-scale fluctuations created atop them. This superposition of fluctuations is a hallmark of cosmic inflation, persisting as long as inflation continues. However, inflation ends randomly and not uniformly. In an inflating universe, nearby regions where inflation ends would be detectable before they disappear from view due to exponential expansion. In a tiny region, perhaps no larger than a hamster ball, space's energy converts into matter and radiation in a rapid, but not instantaneous process known as reheating. This marks the transition from inflation to the hot Big Bang. As the hot Big Bang begins, distant regions expand more slowly over time. From an outside perspective, the expansion rate drops in areas where inflation ends, while surrounding inflating regions continue to expand exponentially. This means regions of hot Big Bangs will expand away from each other, unlikely to ever interact or collide. When inflation ends for our region, the energy inherent to space transforms into a hot, dense sea of particles. Quantum fluctuations during inflation result in overdense and underdense regions, which serve as the seeds of cosmic structures. While we can't observe these early density fluctuations directly, we can extrapolate them from the cosmic microwave background, observed 380,000 years later. These temperature fluctuations confirm the story of cosmic inflation, though inconsistencies between the cosmic microwave background and our current cosmological model suggest that something fundamental is missing. An alternative model, loop quantum cosmology, derived from loop quantum gravity, posits that gravity is made up of particles called quanta, forming the fabric of space-time. In this model, space has a minimum size, the Planck scale 10 circumflex 35 meters, implying the Big Bang couldn't have been an infinitely small, dense point. Instead, this model suggests a different, non-singular origin for the universe. Most of us are acquainted with the classic narrative of the universe's inception, where an infinitely dense, infinitely hot point known as a singularity exploded, creating all the space, energy, and matter that constitutes our universe in an event called the Big Bang. This singularity, with no size but infinite temperature, burst forth, and between 10 circumflex 36 and 10 circumflex 32 seconds, space expanded exponentially, growing immensely in size. After this rapid inflationary period, space continued to expand, but at a much slower rate, eventually leading to the vast universe we observe today. This inflationary Big Bang theory is the most popular and broadly accepted explanation of the universe's beginnings. However, for some physicists, this theory does not provide a complete picture of the universe's evolution. They propose that the universe existed before this singularity, stretching infinitely into both the past and future. According to their bouncing universe theory, the universe was contracting before the Big Bang and began expanding afterward. This Big Bang wasn't so much an explosion as a bouncer moment when a shrinking universe reversed course and began to grow. In this model, the universe could bounce again, with today's expansion followed by a future collapse and another bounce. Some physicists even suggest this bouncing could continue indefinitely, presenting a challenge to the conventional Big Bang view that everything started from a single event. Renowned physicist Brian Cox has also questioned the Big Bang theory, asserting that something cannot emerge from nothing. Complicating matters further, discoveries by the James Webb telescope have suggested contradictions to the idea that the Big Bang marked the universe's beginning, prompting questions about what might have preceded it. Could the universe have begun with a bounce or another process entirely? This issue remains one of the most contentious in physics today, prompting us to delve deeper into the mystery of the universe's true origins. The idea that the universe had a beginning, often referred to as a day without a yesterday, was originally proposed by Georges Lemaitre in 1927. Although it remains plausible to argue that the universe likely had a beginning, this stage of our cosmic history has little to do with the hot Big Bang that describes our early universe. Many laypersons and even some professionals still hold on to the notion that the Big Bang signifies the beginning of everything, but this definition has become outdated. Today, evidence points to a non-singular origin of our universe. We never reached those arbitrarily high temperatures suggested by a singularity. Instead, our universe is best described by an inflationary period that occurred before the Big Bang, with the Big Bang being the consequence of what happened at the end of this inflation. During the inflationary period, the universe was essentially empty, no particles, matter, or photons, just empty space filled with a tremendous amount of energy fluctuating over time by about 1 part in 30,000. As the universe inflated, these fluctuations stretched to larger scales, with new small-scale fluctuations arising. This superposition of fluctuations is a defining characteristic of cosmic inflation and continues as long as inflation persists. However, inflation ends randomly and not uniformly across the universe. If you are living in an inflating universe, you would likely experience a nearby region where inflation ended while the space between